Picture a late-night conference call in 1962. Two superpowers, the United States and the Soviet Union, are on the brink of launching their first intercontinental ballistic missiles. The consequences are catastrophic, and the choices are stark. What ultimately steered the world away from catastrophe was not brute force, but a game. A strategic interaction understood, at least in part, through the language of game theory. This scenario, dramatised in Thomas Schelling's classic The Strategy of Conflict, is a reminder that every strategic decision, whether between corporations bidding for a contract or nations negotiating climate accords, is a game in which the players, the moves, the payoffs, and the information available to each side matter profoundly. The twist and the promise of today's video is that we no longer have to rely on a handful of decision makers and a few intelligence reports. We have at our disposal a complete ecosystem of human talent, men and women alike, vast data reservoirs, and sophisticated simulation facilities. When we bring all of those resources into the model, the game changes, and so does the outcome. So let's first explain what exactly is game theory. Game theory is a way of thinking about the choices we make when those choices depend on what other people are doing. Imagine two friends deciding whether to bring a pizza or a salad to a shared dinner. Each will try to guess what the other will bring, so they don't end up bringing the same thing. In business, companies set prices while watching competitors, and in politics, nations negotiate treaties while considering each other's possible moves. By looking at these situations as games, with players, possible actions and outcomes, game theory helps us predict what's likely to happen, spot better strategies, and understand why sometimes cooperation works and other times conflict does. It's a simple idea. People adjust their behaviour based on what they expect others to do. But it can explain everything from everyday decisions to large-scale international negotiations. Before we proceed, let's quickly recap the anatomy of a game in game theory. Players, the decision makers, which could be individuals, firms, ministries, or entire nations. Strategies, the set of actions each player can choose. In a price-setting competition, the strategies are the possible price points. In a diplomatic negotiation, they are the proposals on the table. Payoffs, the outcomes that each player cares about, typically expressed in utility, profit, or political capital. Information, what each player knows when making a decision. Games can be complete, everyone knows everything, or incomplete, where there is some hidden information. Chess is an example of a game where each player knows everything, as no piece on the board is concealed and the properties and behaviour of each piece is known. Timing, whether moves are simultaneous or sequential, which leads to concepts such as extensive form games. Equilibrium, a configuration of strategies where no player can profitably deviate given the other's choices. The most famous of these is the Nash equilibrium. A Nash equilibrium is a stable outcome in a situation where everyone's choice fits together, so that no one can do better by changing their own decision, while the others keep theirs the same. In other words, each person is already doing the very best they can, given what everyone else is doing. So there is no incentive for anyone to switch. This stay where you are because it's already the best you can do point is the Nash equilibrium. These building blocks are the scaffolding upon which we attach the real-world resources that we will discuss next. When the scaffolding is enriched, the structure we build becomes far more resilient and adaptive. Human capital, men, women, and the spectrum of perspectives. A game model is only as good as the assumptions we embed about the players. Historically, many classic models assumed a homogeneous, rational actor. In practice, decision-makers differ in risk tolerance, communication style, access to networks, and even how they perceive fairness. Gender, for instance, has been shown in numerous behavioural studies to influence strategic behaviour. Women, on average, tend to be more risk-averse in competitive settings, more collaborative in bargaining, and more attentive to the distributional consequences of outcomes. When you deliberately construct a gender-balanced strategy team, analysts, modelers, and senior decision-makers, you bring in divergent priors, richer scenario narratives, and a broader set of behavioural parameters. In a multinational corporation that was preparing for an entry into a new market, the inclusion of both male and female market analysts revealed a hidden payoff dimension. The brand's perceived safety amongst female consumers. Incorporating that insight into the pricing game shifted the equilibrium from a low-margin price war to a differentiated premium positioning, delivering a 23% higher net present value than the original plan. Thus, the first resource is human diversity, a spectrum of gender, cultural background, discipline, and experience. Leveraging it means building interdisciplinary, inclusive teams that feed their various insights directly into the model payoff matrix and strategic sets. Excluding half of the population from your resource pool is not a winning strategy, either at the corporate or the nation-state level. Information, from open data to real-time intelligence. The second resource we're going to look at is information. In the 1960s, the radar stations and human analysts formed the information pool. Today we have open-source data like government statistics, satellite imagery, and social media sentiment. Proprietary databases, customer transaction histories, R&D pipelines, real-time feeds, Internet of Things sensors, market tickers, cyber threat alerts, expert knowledge, consultants, academic research, and field practitioners. Each of these feeds can be modelled as a signal that updates beliefs in a Bayesian game. Consider an online platform that matches freelancers to projects. By ingesting real-time data on freelancer availability, client urgency, and macroeconomic indicators, the platform can continuously recalibrate the matching game. The resulting equilibrium yields higher utilization rates for freelancers and lower vacancy costs for clients, an outcome that would be impossible under static information. The key lesson is that information is not a passive backdrop. It is an active leveler that reshapes players' beliefs, modifies payoff structures, and can even alter the set of feasible strategies. Designing mechanisms to capture, clean, and integrate information while respecting privacy and ethical standards must be a central part of any game theoretic deployment. Facilities, labs, simulations, and war rooms. The third pillar is facilities. In the early days of strategic studies, war rooms were physical tables with maps and markers. However, now we have high-performance computing clusters for running massive, agent-based simulations. Virtual reality war rooms where participants embody different roles and experience the consequences of decisions in immersive scenarios. Scenario labs where cross-functional teams conduct tabletop exercises, iterating through game rounds at accelerated speeds. Collaborative platforms like cloud-based modelling environments that allow geographically dispersed analysts to co-author game trees in real time. A compelling example comes from the Ministry of Defence of a European country that, to improve its cyber deterrence posture, built a cyber range, a virtual sandbox where attackers and defenders could play a repeated game of intrusion versus patching. By populating the range with a balanced mix of male and female cybersecurity experts, data scientists, and policy advisors, the range generated a repository of best response strategies that later informed national cyber policy. The outcome was a measurable reduction in successful ransomware incidents within 2 years. Thus, facilities provide the execution environment where theoretical models meet practical experimentation. They enable rapid iteration, validation, and learning, an essential process for turning abstract equilibria into actionable policies. Now that we have catalogued our resources, let us discuss how to embed them systematically into our game models. Enriching player representations. Traditional models treat players as monolithic entities. To incorporate gender diversity, we can create sub-player structures. For instance, in a bargaining game between a multinational and a local union, the union can be modelled as a coalition of sub-players: male skilled workers, female skilled workers, male semi-skilled workers, and female semi-skilled workers. Each sub-player brings distinct utility functions, perhaps differing weight on wage versus job security. The coalition's collective payoff is then an aggregation, for example a Nash bargaining solution, that respects intra-coalition fairness constraints. This rich representation captures the distributional politics that often decide whether a deal is reached or not. Dynamic information updating. Incorporating real-time data transforms a static game into a dynamic one. The tool of Bayesian updating allows each player to revise beliefs as news signals arrive. Imagine a firm competing for a government contract. As the procurement agency releases incremental specifications, the firm's strategic model updates the probability distribution over possible contract values. The firm can then decide whether to invest in rapid prototyping, which is a high-cost strategy, or to adopt a wait-and-see approach, which is a low-cost strategy. The equilibrium outcome becomes a path-dependent process, sensitive to the information flow. Simulating environments. Agent-based modelling, or ABM, provides a bridge between the abstract game and the messy reality of facilities. In ABM, each agent can be assigned attributes, gender, expertise level, risk tolerance, and can interact on a network defined by organizational hierarchies or supply chain linkages. By running thousands of simulations in a high-performance cluster, we can observe emergent equilibria, identify tipping points, and test policy interventions. For example, what would happen if we did this? The outcome of these simulations can feed back into the analytical game, refining payoff functions and strategy spaces. institutionalizing inclusive decision-making. A practical step is to institutionalize resource-informed decision gates. Before a strategic move is executed, a cross-functional review panel, mandated to have a balanced representation of data, operations and legal experts, must evaluate the game model, the data inputs, and the simulation results. This resource audit ensures that no perspective is omitted, and that the model's assumptions are scrutinized from multiple angles. The result is not merely compliance, it is a higher quality strategic insight. Applications when applied to organizations. Let us now explore 3 concrete organizational contexts, where the confluence of game theory and all available resources yields tangible success. Competitive pricing in a digitally enabled marketplace. A global consumer electronics firm faced a price war in the smartphone segment. The traditional approach, cost-plus pricing, failed to capture the strategic interdependence with rivals. By forming a mixed-gender analytics team and feeding it with real-time market data, price tracking, consumer sentiment from social media, competitor inventory levels, the firm built a dynamic pricing game that accounted for both short-run profit and long-run brand equity. Using a cloud-based simulation lab, the team ran millions of price trajectory scenarios. The Equilibrium solution recommended a tiered pricing strategy that combined premium flagship devices with aggressive discounting of older models, a move that lifted market share by 7% while preserving margin. R&D portfolio allocation across business units. A multinational pharmaceutical company needed to allocate a limited research and development budget across several therapeutic areas. The decision involved multiple internal stakeholders: research scientists, both male and female, marketing leads, regulatory affairs, and finance. By constructing a cooperative game where each unit's payoff reflected not only its own expected revenue, but also the spillover benefits, for example, platform technologies, to other players, and by integrating internal data on pipeline success rates and external data on disease prevalence, the firm identified a shapely value allocation that was perceived as fair by all parties. The inclusive negotiation process, facilitated in a VR war room, led to higher morale and a 15% increase in the probability of achieving at least one blockbuster drug within the planning horizon. Supply chain resilience and risk sharing. A logistics firm sought to secure its supply chain against geopolitical shocks. By mapping the network of suppliers, transport providers, and customs authorities, and by enriching the model with gender-diverse risk analysts, who brought distinct perspectives on political risk and community impact. Thereby, the firm built a sequential game, where each node could choose to invest in redundancy, for example dual sourcing, or to accept a higher exposure. The simulation lab, powered by a high-performance cluster, revealed that modest investments in redundancy by a subset of female-led small-scale suppliers produced a network-wide reduction in expected disruption costs by 23%. The firm subsequently offered capacity contracts to those suppliers, locking in resilience while supporting inclusive economic development. Applications at the national level. Game theory's reach extends far beyond corporate boardrooms. Nations too can harness the full suite of resources to craft strategies that promote prosperity, security, and sustainability. Climate change negotiations. International climate accords are classic, repeated public goods games, with each country deciding how much to contribute to emissions reductions. Historically, negotiations have suffered from mistrust and free riding. By establishing a global data platform that aggregates satellite-derived emission estimates, economic activity metrics, and climate impact models, all countries now have a common, transparent information base. Moreover, the negotiation delegations have been deliberately gender-balanced. Research indicates that mixed delegations are more likely to propose cooperative solutions and to prioritise long-term outcomes. A simulation facility hosted by the United Nations allowed participating nations to play out policy scenarios in a virtual Earth system model. The repeated game equilibrium that emerged, where each country's contribution was linked to a transparent verification mechanism and to a climate finance reward pool, was accepted by 98% of the delegations. The result, the Paris Agreement's enhanced transparency framework and a commitment to a $100 billion climate fund that is now operational. Cyber deterrence, an attack-defender game. In the realm of national security, a dynamic attacker-defender game is played out daily between state actors and cyber criminals. A country that invests in a national cyber range, a virtual environment where both defenders and simulated adversaries can test tactics, gains a decisive advantage. By staffing the range with a gender-diverse pool of cyber experts, intelligence analysts, and policy advisors, the nation captures a broader set of threat vectors and response options. Real-time threats, malware signatures, phishing trends feed directly into the simulation, producing an adaptive equilibrium that informs the nation's cyber deterrence posture. Since the range's inception, the country has reported a 31% reduction in successful ransomware attacks on critical infrastructure. Trade policy. When two countries negotiate market access for agricultural products, they often employ a combinatorial auction. Each country bids for tariff reductions on bundles of goods. By constructing a joint modelling team that includes economists, trade lawyers, and gender specialists, both sides can design an auction mechanism that respects not only economic efficiency but also social equality. For example, protecting smallholder women farmers. Leveraging high-resolution trade data, the teams simulate thousands of auction outcomes. The final design, tested in a sandbox facility, yields an equilibrium that increases overall welfare by 4.5%, while ensuring that at least 30% of the gains accrue to women-owned farms. The agreement has since been hailed as a benchmark for inclusive trade policy. Designing inclusive, resource-rich strategic processes. Having seen the power of integrating people, information and facilities, let us propose a practical framework that any organisation or government can adopt in 6 stages. Stage 1. Resource mapping. Conduct a systematic inventory of internal and external assets, staff composition, data sources, and physical or virtual facilities. Step 2. Inclusive team formation. Assemble cross-functional groups with a minimum gender parity threshold and ensure representation from diverse functional domains. Step 3. Information integration architecture. Deploy a data governance platform that ingests, cleanses, and tags all data streams, with built-in privacy safeguards. enable each team member to query the data in a self-service fashion, fostering data-driven intuition. Step 4. Iterative simulation. Use high-performance computing or cloud-based agents to run a breadth of scenarios. Conduct stress tests that vary gender composition, data accuracy, and facility availability to assess robustness. Step 5. Decision Gate Review. Prior to implementation, convene an inclusive, strategic board that evaluates the simulation outcomes against equity, feasibility, and risk criteria. This board must include both male and female senior leaders and at least one external expert. Step 6. Institute a feedback loop. After the decision is enacted, collect outcome data, update the information base, and rerun simulations to refine the model, creating a learning cycle that continuously improves strategic clarity. When this loop is institutionalized, the organization or nation transforms from a static decision maker into a living strategic engine that will continuously harvest its full resource base to stay ahead of competitors and adversaries. Ethical and practical considerations. The promise of leveraging all resources is seductive. However, we must tread carefully. Bias mitigation. Even a gender-balanced team can inherit biases from historical data. Rigorous bias audits of datasets and model outputs is essential. Privacy and security. Real-time data streams can contain personal information. Strong encryption, access controls, and compliance with legal regulations must be baked in. Resource allocation equity, ensuring that the benefits of strategic decisions are distributed fairly. For example, not concentrating gains in a single demographic. This requires explicit equity constraints in the game formulation. Complexity management. Adding layers of resources can explode model complexity. It is vital to balance a model's fidelity with interpretability. Sometimes a simplified model that captures the key dynamics is more actionable. Human agency. Games are tools for insight, not replacements for human judgment. The final decision should always be the product of informed deliberation, not an automated output. Hopefully you will have found this video of interest, but that's it for today. Thank you for watching.
Thank you for watching today's video. Please feel free to click on the link in the description below to discover more videos.